Thank you all, and I appreciate the invitation to talk to you all today. So Twist, if you're not familiar, we're a DNA synthesis company based on the West Coast of the United States. I lead biosecurity for the company. And in the context of synthetic DNA, what that generally means is treating DNA as what's called a dual-use material. So this is a material that can be used for amazingly positive things, but also, and you've heard some talk about this today, you could make a synthetic virus and try and cause harm with that. So really what we focus on is, and especially in the kind of growth of AI tools lately, you've heard a lot about this idea of bridging the digital to physical. So synthetic DNA represents kind of the first step in taking something from a digital design and transitioning that into the real world. And so the companies that have the technologies to do that synthesis take it very seriously and ensure that the customers that we serve are going to use those materials responsibly. All right, so I'm going to start out by giving kind of a brief background about where kind of the biosecurity awareness in the synthetic DNA industry came from, and then sort of pivot from there to how DNA data storage might think about these same issues. So a lot of this goes back to, in 2002, Eckhard Wimmer used oligos to essentially stitch together the virus, or the genome from the poliovirus, and to rescue live virus. And he did that in a background of the WHO working diligently on eradication of that virus globally. And so the point he was making was like, yes, you can eradicate it in naturally occurring reservoirs, but synthetically you can just recreate the virus, especially for viruses like polio that have really small genomes, so 7 kb. As you might imagine, that caused a lot of attention on the part of governments, civil society. There was a flurry of reports and activity, and this was happening in a background of technological capability development. So nucleic acid synthesis companies at the time were starting to be able to produce gene-length DNA for the first time. And so you had this concern matched with an increase in capability. So this really all came to a head in 2006. A reporter from The Guardian ordered a very small piece of smallpox. So if you don't know, smallpox is an orthopox virus, has a very large genome, 200 kb. This reporter ordered a very small piece of it and then wrote this incredibly exciting sounding story about the irresponsible synthesis providers that were out there making this stuff and just handing it out to everyone. And this really, I think, built a lot of attention on the industry side in terms of what you might think of as reputational risk. There was a wide awareness, even in the government side, that this didn't pose a threat scientifically or biologically, but it certainly posed a threat reputationally. And it really got industry and governments and civil society kind of all around the same table, spending a lot of effort to talk through these issues. So there was a series of meetings that were carried out, and one of the things that came out of those meetings was the formation of this group that Sophie mentioned, the International Gene Synthesis Consortium, which I currently chair. At the time, this was just 5 companies, the largest synthesis providers in the world at the time. And the goal was to really coordinate. So while those companies are bitter competitors in the marketplace, the goal was to coordinate on biosecurity best practices. So in 2010, the US government released a guidance document that essentially canonized, canonized recommendations that the government and the national security side had for these companies, saying you should screen your customers, make sure they're legitimate. Now what that means is something we can all argue about, and we have, but that is a good goal. You should screen the sequences so that you make sure you know what you're being asked to make. You should also alert, in the case of the United States, you should call the FBI if you think if there's anything suspicious. That should be your first point of contact. And you should retain all of the records of this activity for 8 years, so you have some ability to go back forensically. So 15 years go by. Technology continues to advance. You have costs coming down, throughput coming up. There were startups that were working at benchtop synthesis, Sophie mentioned. There was an organization in the US, IARPA, they funded quite a large program to actually improve the tooling around being able to do this kind of sequence screening to predict biological risk from primary sequence. The IGSC during that period grew to about 40 member companies. We got a new fancy logo. And we continued engagement with government. So there's been an ongoing discussion between industry and government. So it has been really productive and healthy. So in terms of where we are now, in 2023, Sophie mentioned this, the US updated its guidance. One of the key things that it did was to take, in 2010 it had said if the sequence is smaller than 200 base pairs, don't worry about it. And we just had a question about, well, couldn't you make a virus out of 49 base pairs? I do want to mention that the goal of all of these practices is not to eliminate risk. It's just to make it much more difficult to misuse things. So I don't want you to see any of the things we talk about today as a complete bulwark against misuse. The goal is really to make it as hard as possible. And so the government, the US government, recognized that we should maybe move that 200 base pair threshold down to 50 base pairs. Let's make it even harder. And importantly, that guidance did not address DNA data storage at all. There's no mention of it in that document. In 2024, the US released a formal framework. It essentially said, you, the synthesis companies, need to publicly attest that you do these 6 things. And if you do that, we will allow organizations that receive US federal R&D dollars to buy synthetic nucleic acids from you. So this was the first time that a government was trying to use economics as an incentive for biosecurity practices, which industry has asked for a long time. This was really important to be an important step that I think the US government took. And then the UK government, in that same year, published their guidance document, which very closely aligned with the US guidance. And that's also really critical for industry. This is a hugely international market. So companies based in the US serve the world, companies based in the EU serve the world. And so we really want as uniform a global playing field as possible. So having countries align in their guidance is actually extremely valuable. This year, the new administration in the US decided to rewrite the 2024 framework. So there's active engagement within the IGSC with the current government to say, here's what we liked about the framework, here's what we didn't like. So we will probably see some changes coming to that framework. And as Sophie mentioned, the EU is currently working on this Biotech Act. And I also want to say AI tools have thrown a wrench in a lot of this. So most of the tooling around sequence screening and risk assessment rely on homology. So is this similar to some virus that we know and understand? And a lot of these AI protein design tools allow you to try and preserve function, but eliminate homology. And so now we're kind of thinking about what tooling will we need to go up a level of abstraction to say, can this thing do something that we know is harmful, regardless of whether it shares a lot of direct sequence homology with something from a pathogen? So the IGSC today, we have monthly meetings, we share best practices, we share concerning experiences. So if anyone has a customer that approaches them, the goal here is to prevent venue shopping. You don't want to have customers just look around and try and find the lowest common denominator. The IGSC produces this harmonized screening protocol. We try and teach everyone, here's how to screen uniformly in a way. We provide data resources like this, what we call the restricted pathogen database, suspicious order reporting forms. We have a test set working group that's been working with the National Institutes of Standards and Technology in the US, along with IBIS, around how do you even test systems like this for performance. And then at Twist, just to affirm, we screen every customer that comes up to us, we screen every order that's placed with Twist to make sure that that material is going to a responsible party who will use it responsibly. Okay, so given this whole landscape, what does that mean for DNA data storage? So I would say that one of the things that's been most wildly successful over the past 20 years has been this like community-led engagement with governments and civil society. And so I would certainly recommend that this community try and continue that model. I do want to clarify what we're talking about in terms of a threat model for the sort of scenarios that follow. This is someone walks up to you and says, I have a pool that I want you to make for me. Here's 1 billion oligos. But I've put secretly 200 oligos in there that will assemble into something that can be misused. And so the question is, how do you construct your services, your products to avoid that entirely? Or then how do you put systems in place to defend against it? And then how do you build confidence with regulators that you've put all these systems and practices in place to make sure that the technology is not going to be misused? part of the issue, even at gene synthesis scales, which are way smaller than the kinds of numbers of unique sequences that you'll need for DNA data storage, sequence screening is expensive. So up front, I would say what we really want to avoid is the need to carefully screen DNA storage pools to look for potential risk, because it's going to be really expensive versus the price that the market is likely to bear. And so what you want to do is remove the need to do that entirely while building confidence that that's not going to be subject to misuse. But even if, we heard some talks yesterday about really interesting uses of GPUs and FPGAs to do computationally efficient algorithmic implementations, even if you could do that for screening, you still are left with the interpretation of the screening results, which are really complicated and generally require a PhD level skill set to interpret, and even then are left to sort of the moral decision making of the observer to say, is this something that crosses my threshold for whether I'd be concerned or not? So I think there's three models that can possibly work here to sort of remove the question of whether you need to worry about this or not. And the first is just a sort of trusted device or trusted party. So this is a one-stop shop. You send binary data in one end, DNA sequences come out the other. You don't have control over the pool. And so that allows you to say that I know at least intent-wise there's nothing in that pool. I know we've talked a little bit about incidental homology. And personally, I'm not worried about incidental homology, largely because if I have a pool of 50 billion oligos and I don't know what homology might be in that pool, it's very difficult for me to figure out a way to misuse that incidental homology. So I know there's been a lot of work that Catalog and Biomemory have done to try and eliminate that risk way upstream in the encoding step. But I would argue that even if you don't do that, as long as you don't allow any input into the pool in terms of its definition, the risk remains extremely low in terms of misuse. And I think this route is actually the easiest to explain to a policymaker, which has distinct advantages. You can also think of like a trusted storage or a custodial model where an actor comes to you and says, here's my pool, my billion oligos, please make it for me. And you say, sure, I'll make it for you and I'll store it for you. I won't give you the physical material. And then when you want the data back, let me know and I'll recover it for you. And so in that case, you're not actually turning the physical material over to the actor, and so there's no potential for misuse. But this, again, this is easy to explain to a regulator, so that's good, but it does require a single actor to be synthesis and storage provider. And then there's a model where you might think of kind of trusted parties, so a small number of companies interacting with one another. You might think of somebody doing the encoding, someone doing the synthesis, someone doing the archiving. Those organizations all have to have a very high level of trust. They have to have processes in place to detect potential bad actors, and they have to be able to demonstrate the fact that they have these mechanisms in place. There we go. The challenge with this is it's actually really complicated to describe to a regulator in a way that makes it seem totally divorced from misuse. And so it will require a pretty high degree of kind of political and ongoing education to make sure that the technological implementation is something that regulators can buy into. So I think those three models kind of form a solid basis for engaging with governments. And I would certainly recommend that you all, as Sophie said, start having those conversations, because I do know that, especially at least in the US, there's starting to be some discussions at quite high levels of DNA data storage, and should they think of it in line with all the other risks that comes with biological uses of DNA. And my hope is that those two things are not lumped together, because the costs associated with screening are just so high compared to the eventual margins for data storage. So with that, I will leave it there and take your questions. Thank you.
Hello, thanks for the presentations. One of the benefits of chemical synthesis, you can also use like non-biological bases. So is it something that can be included? And also, because we don't code for biological elements, can we also remove one of the biological bases, so working with 3 instead of 4, or the modified one? Is it something that can be explored?
I think anything you can do to convince regulators, civil society groups, others that are engaged in these problems that your product is abiological and does not pose biological risk is good. If that involves non-canonical bases, great. If you reduce the base count, great. But the goal is really to make sure that these two things are not treated similarly in the minds of, both in the minds of regulators, but also in the minds of the technology developers that are putting these things together, that it is literally not subject to misuse, potential misuse. So that is one way of dealing with that.
Thanks.
Hi. If I got it right, the cost comes from calculation on-site from the, let's say, for Twist or its competitors. Is there a way to oblige the customer to basically download the software that it cannot modify and do the screening himself and then send a certificate to your company, so then you can start the synthesis?
There have been discussions, not just in the data storage side, but even in the biological use case side, of that kind of trusted representation of some kind of proof. I think the challenge is the way that data is currently transferred between parties is all over the map. Word files, text files, Excel files, and those things are really hard to secure against manipulation. If you had a system that was, hashing files and verifying unalterability and things like that, I think that would be fine. The challenge is really broad adoption. So remember that this is, there are maybe a dozen very large, sophisticated companies that do this, but there's a very long tail of much smaller companies that have capability and are willing to make gene-linked DNA, but may not have kind of these sophisticated practices. And so what you want to make, like IBIS make the common mechanism to address this particular case, you want very simple solutions that can help people reduce the risk of misuse. And something like this, while it may work, it'd be very hard to get it to be uniform globally.
James, you mentioned that the cost of screening is very high, so we are not operating synthesis company, so we don't know what this very high means. And my question is, if the regulator considers DNA storage is not exempt from screening or for whatever reason and regulates and requires screening of all sequences, what would be the consequences for the development of DNA data storage technologies in your view?
So cost is relative right now. So the actual cost of screening for the price you pay for biological use cases for synthetic DNA is not something we're super worried about. But the challenge is when you start to need 3-4 orders of magnitude more unique sequences, then the cost per sequence actually, or per base screening, becomes a real issue, especially at the cost that the market looks to be willing to bear for DNA data storage. So I don't want to sound like I'm making the current thing sound expensive. It's not, but for this use case it is. And then the challenge with having regulators come in and say, you should do this, I do think that it would create a new problem, which is you have to go find slightly faster ways of doing this kind of homology searching. But it would also link you to an emerging problem, which is we're starting, and I got to this a little bit in the talk, we're starting to move away from homology as being a good indicator of biological risk and moving towards much more abstracted ideas of like, am I reproducing protein function that is useful in a context to cause biological harm? And so what you don't want to do is yoke DNA data storage to this emerging really difficult problem and drive even higher costs of screening and even more regulatory uncertainty. You really want to make it very clear that this is an abiological use case for DNA and there is no risk.
Okay. We will, I guess, continue this discussion about biosecurity during the panel discussion this afternoon. I've got many other questions, but we'll have opportunity to talk about this. Thank you very much to all speakers of the session.
Thank you all.